Okay, so let's recap what we learned last week. Last week, we talked about some part of the MIMO, multiple antenna systems, right? And as you know, in multiple antenna system, we always start from this simple model, like HS, the Y, the receive symbol, receive matrix in this case, Y equal to HS plus N, which is this one. Remember, the Y and H and N, these are capital letters, meaning that these are matrices. Okay? In case of SIMO, single antenna, single input and multiple output, there are several ways of running this SIMO. Okay? And this picture basically shows you one example, how we can take advantage of multiple receive antennas, right? We transmit only one symbol because we have one antenna. But that symbol is received by two different antennas. And one thing that I need to mention here is that when you have two antennas, the receiver, right? You want to make these two antennas as much separated as possible. What that means is if you collocate these two antennas next to each other, that basically means that this transmitted symbol may be received by the two receive antenna with the same symbol. Okay? If both antenna receives the same symbol with the same form, then what that means is that there are high correlations. Okay? Receive symbol Y1, another receive symbol Y2, if those two are same or very similar, very close, that means we have a high correlation. When you have a high correlation, then you have pretty much no advantage by having two antennas, right? So you want to make Y1 and Y2 as independent as possible, right? In order to make these two symbols to be independent, what you need to do is that spatially, we have to make these two antennas separated. Okay? You want to make these two antennas to be separated in spatially. That way, think about the distance between these two are pretty large. In that way, the receive symbol Y1 is kind of reflected from this area, whereas the receive symbol from the second antenna is reflected, is traveling with a different path. Traveling with a different path gives you some independence between these two receive symbols, right? So that's one thing that you have to think about. And there's a certain theory based on the distance, based on the minimum distance between these two antennas to guarantee the independence between these two. Okay? The rule of thumb is that if the distance between these two antennas is larger than half wavelength, right? Half wavelength, then you can somehow achieve the independence between these two, or less correlation. Okay? That's a rule of thumb. Okay? Half wavelength, half lambda. Anyway, that is the basic assumption here. Now, what we can see is that when you have two antennas like this, right? And again, we assume a Y1 and Y2 are independent. In that way, you see that the Y1, the receive symbol from the first antenna, is shown as a blue, and the second symbol, let's say, is green. Then in this picture, basically shows you that I want to choose the best one. As time goes, right, I want to choose the best one. At this time, this is time. At this instant time, I choose a blue because blue is better than green. And as time goes, at this particular case, I choose green because green is better than blue now, right? So you can always choose the better one. Then eventually at the output right here, okay, right here. So this is blue, this is green, and right here you see that this is here is red, right? So you see always the maximum. You choose the better one, so that is what you achieve here. Okay, so the red curve is the channel SNR you can achieve right here. This is one example of how to use the two receive antennas. And this is typically called the selection diversity because you select a better one, right? Mathematically, it can be written this way. So that's one example, right? So that is a selection combining that we just mentioned. But there are other ways to do it. Maximum ratio combining, equal gain combining, switch combining. We already looked at this one last week. Probably the maximum ratio combining is probably the most basic and most important things. Okay? And the concept about the maximum ratio combining is that you are multiplying certain weight for each antenna or each signal. Okay? We are not ignoring one and choose the other. Okay? We are not only selecting just one, we are using both of them. But Y1 and Y2 are not the same. They are independent, first of all. And sometimes Y1 is good, Y2 is under deep fade, meaning that Y2 is bad, right? In that case, you want to multiply a certain weight depending on your Y1 and Y2. If a Y1 is good and Y2 is bad, or high, low, that means you want to multiply some maybe large gain onto the Y1 and small gain to the Y2, depending on your Y1 and Y2, right? Remember my CEO example last week, right? I'm CEO and I'm manager, let's say, and I have two guys working for me. And one guy has a very high performance, and there's a second guy has a very bad performance. In that case, I'm going to give him more job because he actually works very good, right? He works very fast. He has a good performance, so I can give him more job, more work, and I can give the second guy very small work because that's the only thing he can have, right? So that's kind of weight. That's pretty much, you can guess that that's probably the maximum or optimal way to assign the jobs, right? What I want eventually as a manager is to finish as many jobs as possible, as many work as possible. But to do that, I have to give the high performance job, high performed guy, large amount of work, low performed guy with some small amount of work. That way, if I add these two, that will maximize the total amount of work. It's the same concept. Now then, mathematically, right, how to achieve gain, the omega 1 and omega 2 is something like this. Okay? The goal here is that we want to maximize SNR right here. Okay? Signal to noise ratio right here. We have a signal to noise ratio of the first antenna signal. We also have a signal to noise ratio from the second antenna. But when you multiply a certain gain, okay, and add it, we want to maximize the SNR right here. Now, one question here. When you multiply some gain, okay, certain gain onto this signal, okay, then what happened to the SNR for the first signal, first antenna signal? When you multiply some gain, okay, your SNR does not change, right? Because you multiply certain gain onto this first receive signal, right? But this amplification also impacts your noise. Right here in the Y1, right? Y1 is the, where's Y1? Y1 equals to H1S plus N1. So when you multiply W1 to Y1, that means you are amplifying the signal, you are also amplifying the noise with the same factor, right? SNR does not change. What is SNR? SNR is the signal power divided by noise power. So both of them, okay, both of them are amplified, right, by W1. So the SNR for this guy does not change. Same here. But SNR for this guy does not change. SNR for this guy does not change. But when you add it together, right here, we want to maximize the SNR when you add these together. Okay, that's what we want to do. In order to do that, what we are dealing with here is complex value. That's one thing that you want to remember. We are dealing with a complex value. Y1 is complex. Y2 is also complex. Omega 1, omega 2 gain, these are also complex. Okay, we are all dealing with complex values. So when you multiply W1 here, right, then you are right here, right? Again, it's complex. Here again, it's complex. So when you add these two complex, okay, how can you maximize the power here, or SNR? In order to do that, right, this value right here and this value has to be aligned. Okay? Think about the vector. If this value goes to this way, this direction, and the second one goes to another direction, then when you do the vector sum, that goes to some other direction, but you see that now the amplitude or the signal power is not maximized. The only way that the signal power here or SNR is maximized is the case that these two are aligned onto the same direction, right? That way you add these together, you know, those are aligned. So what we need to do is that we need to make these two outputs to be aligned with all in the different, all in the same line, okay? That's what we want to do. So in order to do that, you see all these equations, W1 has to be a function of H1 complex conjugate. W2 has to be H2 complex conjugate. This one, right, the one that you see in the denominator, H1 square plus H2 square, those are normalization factor. Typically, this is gain, and you want to multiply the unit gain. The power of the gain is 1. So in order to normalize this gain value, we have this, right? But remember, this H1 square plus H2 square, this is constant, okay? You can multiply any value. Still, it's aligned, okay? In order to make these two outputs to be aligned, what you need is this one, H1 complex conjugate, H2 complex conjugate. If you select W1 equal to H1 complex conjugate, W2 equal to H2 complex conjugate, then these two will be aligned, right? This factor is only the normalization factor. So we can visualize that in the next slide right here. You see that the output right here, right? Output right here is purple, and the output right here is green. And if you add together now, purple and green are aligned on the same real axis. So when you add together, now the total sum is going to be yellow. So it's if you see that the size or the length of the arrow is now maximized by doing this, by making these two aligned. And in order to make alignment, W1 and W2 has to be chosen into this way. Okay, that's the concept of maximum ratio combining. But simply speaking, right, you need to think about my CEO example. Okay, I have two different guys with a different performance. I have to give each of them a different amount of job. That's the gain. And how much different? That's this much. Okay. Equal gain combining is another one. This is not so popular, not that popular. The only difference between the equal gain combining and the previous maximum ratio combining is that this W1 and W2 is no longer, this one has a size of 1. If you go back to the MRC case, right, this W1 is H1 complex conjugate divided by this one. So if you see this one as a constant, right, then you see that this gain is try to cancel out this H1. And W2 is try to cancel out the H2, right? But the W1 and W2 actually has a different gain like this, right? But in equal gain combining, as you see that this W1 and W2 has a unit size. Okay, this one, its size is 1. So that's the only difference. Other than that, this equal gain combining is also try to make these two outputs to be aligned, as you see in this picture, right? Purple and green both are on the real axis. When you add together, we achieve yellow. Yellow is the output SNR right here. Selection combining is what we looked at in the previous slides. In this case, you are selecting the best antenna, right? We are choosing only one. We use only one at instant time. We are not using both. In the previous MRC and EGC, we are using both of them, okay? Using different gain, but we always use both of them. Both are active. But in this case, in selection combining, since you are select one of them, only one is active, the other is inactive. Okay? As time goes, you may want to choose the other one depending on your channel, but at one instant time, you only select one. Okay? So mathematically, your Y, right here, Y can be written this way. You multiply W1 to the first symbol, and you want to multiply W2 to the second symbol, and after that, you choose the best one. You basically compare the output of these two and choose the better one. Okay? That's a selection combining, and you see that this is a illustration, and this is the gain for each of them. We also talked about the switched combining. This is another way to do it. The motivation of this switch combining is that we set a certain threshold. In this case, it's called gamma t. And gamma t is a certain SNR that I think is reasonable. I think is reasonable. I think is a value that gives us a reasonable performance. So what that means is, as long as my SNR is higher than this threshold, then I'm okay. Okay? I don't have to try to get a maximum SNR. You know, maybe this much SNR. As long as my SNR is higher than this gamma t, I'm good enough. So that is the motivation. So this select switch combining has the less number of switching, antenna switching, compared to the selection combining. In this selection combining, right, you always try to find the maximum or always try to find the better one. So as you see in this picture, you switch. You are using green, right? You are using blue right here. But at this point, you switch to blue. No, I'm sorry. This is, you started from blue, and from here, at this point, you switch to green. And you use green, and right here, you switch back to blue. Switch to green, back to blue, right? Something like that. So you switch so many times because you always try to find a better one, so you switch it back and forth many times. But in this case, in switch combining, you are not switching that often because I don't want to find the maximum. As long as my signal is good enough, I'm stay with that. Okay. So in this case, you have less amount of switching, less number of switching. In fact, the switching is also some headache, right? Some overhead, right? So that's the motivation of switch combining. You can reduce the number of switchings. We also looked at some transmit diversity. Transmit diversity is interesting in practice because that typically transmitter is like a base station. You have a lot of power budget, you have a lot of resources, and also space budget. So you can put as many antennas as you like. Whereas in receiver, typically it's your device, mobile device. So you have a mobile device right here that's pretty small. So we cannot put multiple antennas. Okay, so that's why a lot of people are interested in transmit diversity. And among these several diversity combining systems, transmit diversity typically is used for MRT. All the other equal gain combining, selection, these three concepts can be still applied to the transmit diversity, but these are not really much interested in practice because, as I said, these three systems are trying to reduce some complexity. If you forget about complexity, if you don't care about complexity, then this MRC is always the best. MRC gives you the best performance, best everything, except the performance, except the complexity, right? So equal gain combining is trying to reduce the complexity a little bit by choosing the equal gain. Selection combining and switch combining, you are trying to use only one antenna, right? And then you actually save a lot of complexity. So these three are low complexity version in a certain different way. But in this case, right, transmitter, they don't care about complexity. So these are not much interested. We only interested in MRT. MRC and MRT basically is the same. Since we are talking about transmit diversity, we simply call that as MRT instead of MRC, but it's basically the same thing. If you look at this picture, right, this is pretty much a mirrored picture compared to the MRC, right? We have two transmit antennas here and one receive antennas here, but the picture looks exactly same, only in the reverse way. In order to do this MRT, what we have to assume is the channel state information is available at the transmitter. The reason is that if you remember the MRC case, maximum ratio combining case, what was the optimal gain? This optimal gain, for example, the omega 1, right? This omega 1 equals to H1 complex conjugate, which means that you need to know the H1 and H2, okay? You can apply the same thing right here. In fact, in this case, as you see here, the optimal omega 1 is H1 complex conjugate. Optimal omega 2 is also H2 complex conjugate. So we get these optimal gains, okay? But in order to apply this in practice, omega 1 is, let's say, H1 complex conjugate, then this guy has to know H1 and H2, right? Remember, we keep saying the CSI many times, right? Earlier, when we talked about multiple antennas in the previous weeks, we mentioned the CSI is available at the transmitter many times. In this case, right, this is a very strong assumption, as I said, because only the receiver can measure this H1 and H2. So you have to send this information back to the transmitter. So we need to have a feedback channel. That way, the transmitter knows H1 and H2 and apply that H1 conjugate here, H2 conjugate here. So typically, right, when you have a multiple transmit antenna and we have a one single receive antenna, this is the case of beamforming. Okay, this case we call that as a beamforming because we have a multiple antennas here and you apply the different gain for each of them, right? That basically means that you are trying to make a certain beam. That beam is directed towards the receiver. So you are making beam, okay? And that beam is forming directly to the receiver. So this type of signal processing is called the beamforming. In certain cases, beamforming and pre-coding or pre-filtering, those are same concepts, okay? So somehow this maximum ratio transmission is a part of the beamforming, okay? It's like conceptually the same as beamforming. The goal of beamforming typically is to find out the gains, okay? And as you see here, like in the equations, the gain W1 and W2 can be obtained this way. Okay, once you do that, then you can maximize the receive SNR right here. We also learned the space-time block coding. One of the main advantage of this type of space-time block coding is that you don't need to have a feedback channel, right? Remember, that is the main advantage, which means that we can run this one as open loop. This is open loop, right? Because what you do at the transmitter is that just simply collect the two symbol two symbols, S1 and S2, during the two symbol time, and then encode S1 and S2 using these two antennas this way. So this is a way of encoding, okay, called Alamuri encoding. And then transmit over this channel, and you receive those symbols and do the decoding. And how to do decoding is that you already know H1 and H2 by channel estimation, and using this H1 and H2, you construct this matrix, okay, and multiply this matrix into the received symbol. Then you can recover R1 and R2. This R1 and R2 is only a function of S1 and S2, okay? So therefore, you can recover this one perfectly, not just perfectly with the maximum performance. As you see here, it shows the H1 square plus H2 square, which means that you achieve the 3 dB gain compared to the single receiver. In the single receiver case, right, you only have one H square. But in this case, you have H1 square plus H2 square, which means that you have a double performance, right? In other words, 3 dB gain. That means it's achieved the optimal performance without knowing any channel state information at the transmitter. So that is the main advantage of doing this. Okay. So this picture shows you the bit error rate when the BPSK is used. The blue curve shows you the BPSK in Rayleigh fading channel, whereas this red one shows the BER, bit error rate, in case of 8WGN, Gaussian noise channel. Okay, as you see here, that the blue one is actually much worse than this 8WGN case, right? And if you compare the BER of different diversity systems, then you see that the maximum ratio combining is actually the best one. This red one is the maximum ratio combining that actually achieves the best BER performance, and equal gain combining is a little bit worse. Selection combining is a little bit more. Okay, you have a little bit more loss because in selection combining you use only one antenna. We also looked at this BER, the rephrasing BER. We start from these basic BER equations, right? And you use some of the approximation, some Gaussian approximation, some of the Q function approximation like this, and replace the Q function to the exponential and bring that in here, right? And use this Rayleigh fading channel. Then you can reformulate that in here, and using some approximation like high SNR, then you can eventually change the BER equation to this way, right? And remember that the power exponent of SNR is called the diversity order, and this part is called coding gain. So when you increase the diversity order, what is the best way to increase the diversity order? We are talking about multiple antenna system, right? So you increase the number of antennas, that means you increase the diversity order as much. You increase the diversity, you increase the antenna from 1 to 2, then simply speaking, you are increasing the diversity order from 1 to 2. So this picture basically shows you the BER of different diversity order. The blue one is the case of diversity order 1. This is the case of diversity order 2. This is the 4. Okay? So you see that now the BER is increasing much faster rate with higher diversity order. And another way to reduce the BER, bit error rate, is to increase the coding gain. So if you increase the coding gain, now the diversity order is not changed, then your shape, your slope does not change. Okay? This is the case of diversity order 1. So this slope still same because we didn't change the diversity order. We only changed the coding gain right here. Then this whole this curve is now just shifted to the left side. Okay, that's how the BER is affected if you increase the coding gain. So what is the way of coding gain? What is the way of increasing the coding gain? you use some other encoding with high protection. So for example, if you use a turbo coding, okay, or some higher order convolutional coding, in that case, you increase some coding gain, right? Because you are using another encoding in another code with higher protection. In that case, the BR function is now shifted to the left side. Okay? Same way, if you use a higher protection coding with the diversity order 2, then again, this is the case of diversity order 2. We don't change the slope, but the whole curve is now shifted to the left, okay, by using the higher protection code. Okay? Today we are talking about some performance analysis. Okay? Performance in this case is defined by bit error rate or symbol error rate. Okay? We are talking about error rate. When we talk about wireless systems or any other communication system, right, we always talk about error rate. Simply speaking, right, our goal is to minimize the error. Simply speaking, right, we want to reduce the error. That's our fundamental goal. So in order to do that, there are several ways of technique. The diversity technique, spatial diversity, with diversity order 2, increasing the diversity order, that's one of the best ways of reducing the error rate. Okay? But what we are trying to do today is how to analyze the performance. What is analysis? Some people say that, why do we even think about this difficult mathematics? We can do a simulation, right? Some people do that. Maybe that's true, right? You can design your own system, okay? And then you can run the simulation using MATLAB or some other simulation tools. You can always do simulation, right? Once you do the simulation, definitely you will get some performance. Maybe you get your own PER or error rate or anything based on your simulation, right? So then, why do we ever think about such kind of analysis? There are so many different mathematics, and sometimes it's very difficult to do it. You can do simulation, then why do we ever think about analysis? Some people say that other people, they do not believe simulation results. Why? Now let's say you develop your own system, you do simulation, right? And you show the nice result, simulation result. And how do you convince other people that what I designed actually is one of the best? Other people are not convinced based on your simulation results, because you may make your own system. Maybe that's not optimal. Maybe that's just one of the many systems, right? You cannot convince it that way. Other people sometimes even think that what you show maybe is a fake. Who knows, right? So what happened is that that's why some other people are thinking that we need to talk about analysis. Okay? When you think about some system or design a certain system, then you have to approach with the analytic way. That way you show the analysis. There are certain tools, right? Mathematical tools that we use. Using those tools, mathematical tools, and apply your own design into that and do analysis, mathematical analysis, which shows you a nicer curve based on mathematics. Okay? Then many other people actually believes your result, because there's no fake there, right? That's based on the mathematics. Okay? It has to be like that. Okay? So that's why the people, and also not only that, when you do the simulation of your own system, you want to show the analysis together. That way, what you can show is that here's my analysis, here's my performance based on the analysis, and here is my error rate based on the simulation. Sometimes these two are not the same. Because analysis, when you do the analysis, sometimes we may have to do some ideal assumption, because otherwise the analysis may not be possible. Okay? So using some of the assumption, that's also possible, and then you can achieve some performance based on analysis, mathematical analysis, and that's the guideline, or that can be a reference. Okay? Compared to that, here is my simulation. Okay? Then there may be a gap. That gap shows you how much your simulation or your system is, how good your system is, right? If both of them are same, that means your system is pretty good, even in the simulation. Okay? So in other words, analysis can be a reference for your system design. Okay? So what we need to do and what we want to do today is to learn how to do the analysis, how to do the performance analysis of a system, of a communication system. To do that, we first have to look at some of the basics of error probability, okay, bit error probability. So we have to start from a modulation. Among those many modulations, BPSK or binary transmission, binary modulation is probably the best, the simplest one. So we can start from BPSK with antipodal signal. What is antipodal? Antipodal signal is like reversing sign, right? Positive, negative, positive, negative. That's the antipodal signal. So if you plot, this is the time domain plot, and if you plot this one into the constellation domain, this one is a constellation domain. You have a positive value, you have negative value, okay? Since this is a BPSK, both points are on the real axis, okay? So you have some positive energy, negative energy. Remember that you see that the root square E of B. E of B is the bit energy. Each bit has a certain energy, right? Energy is a power. Energy is a square of that, right? EB of energy. So if you think about the amplitude, that it's going to be a root square of EB, root square of energy, right? So you have positive, negative, like this. And first of all, we start to look at y equal to Sn. What that means is we are ignoring fading. Or in other words, we are only considering HWGN channel. That's what this means, okay? We have no fading, no H. We are only thinking about noise. So what this means is that you transmit some signal. This is your own signal, transmitted signal. And you are transmitting one of these, like this, right? You are transmitting plus EB, plus, let's say this is 1. You're transmitting plus 1, minus 1. Minus 1, plus 1, right? Something like that. So that's S. When you transmit this plus 1, minus 1, now it goes through the channel, and that particular channel is HWGN channel. So that channel is adding the noise, right? So therefore, if you think about the received signal, Y, now you see that this is what you transmit, but when you add the noise, now it's like it's noise, right? You have a noise on top of this, right? You have some of the Gaussian noise. Okay, that's our setup. Now, how to analyze the bit error rate of a BPSK is that we show this hypothesis, right? And here is S1, which is this one. And here is S2, which is this one, right? So you are drawing a Gaussian distribution for each of them, right? Because this is what you transmit, for example, like this. This is what you transmit some other times, maybe like this, right? And since we have noise right here, noise, when you have noise, let's say you transmit this one, but when you have a noise, some Gaussian noise that's being added, then when you receive that, then you may receive some point like here, right? Because of noise. This much is noise in that case. Or some other times you transmit this one, but you receive this symbol because of noise, right? So if you think about so many of them and look at the statistics, now we see that the error statistics is Gaussian, right? So what can happen Now you know that the Gaussian has the infinite tail, right? Infinite length tail. So what that means is if you transmit this one, then this one may be received by this symbol with some low probability, right? That happens to be an error. Because when you do the detection for BPSK, right, we cut it here in the half, and whatever received onto the right side, we detect it, we consider that as this symbol, right? So if you transmit this one, and because of the noise, if it is received right here, now this one is considered by this one, considered as this one by the receiver, so that is the error. So this picture basically shows you the error probability, such a probability right here. So this red area and this blue area is the probability of such errors. And now as you see here, this is miss error probability, this is false alarm probability, right? And everyone knows that this Gaussian distribution, and especially this area, right, error probability can be written as a Q function. What is a Q function? This one is a Q function, right? If you think about a single Gaussian distribution, right, and you pick a certain point, and I want to calculate the probability that is higher than this, right, higher than my value right here. And let's say, okay, this is my threshold, and if I want to calculate the probability that is higher than this, that is shown as a Q function like this, right? Now, what you want to see here is that what is important right here in the bit error rate? What is important is that the distance between these two symbols. That's important, right? Because you have a Q function, you have a Gaussian distribution here and here. If you think about a large distance between these two symbols, right? If you think about large distance, that basically means that these two Gaussian shapes are now separated much further. Therefore, this error is getting smaller and smaller, right? If you put these two Gaussian distribution close enough, okay, bring these two close enough, then you see that this error region is getting bigger and bigger, right? So therefore, this error probability is a function of the distance between these two symbols. Okay, the distance between these two symbols, let's say we call that as d, and d in this case, d equals to 2 times of energy, root square of energy, right? That's the distance between these two symbols. And as you see here, the bit error rate, in fact, can be written as a Q function, and the parameter inside the Q function is a function of distance. Okay, we have distance right here. Okay? So in other words, if you increase the d, that means you have a lower bit error rate. Okay, so that's the case of BPSK. And eventually, if you put these together like this, right, then you see that BER of BPSK can be written as Q equals to Q root square of 2 SNR. So this EB divided by NR, this is SNR. EB is the bit energy, and NR is noise power. So EB divided by NR is SNR, the bit SNR, right? So this is the error rate of BPSK. We can also think about orthogonal binary transmission. Antipodal binary transmission was the case of +1, -1, +1, -1. But the orthogonal case is like +1, just 1, 0, 1, 0. That's the case of orthogonal. Okay, in that case, as you see here, 1, 0, 0, 1, 0, 1. Okay, and if you look at the constellation plot, it shows it this way. You have 1 here, you have 0. But remember, in this case, 1 corresponds to root square 2 EB, right? Earlier, it was root square of EB, but in this case, a 2 EB. Why is that? Because what I want is that when you normalize, when you average it out, right, total energy should be same as EB. But in earlier, when you think about the energy, right, total energy, then you do square. Then this all the minus EB square now come back up, and you have EB all the time, right? The average energy should be EB. But in this case, it's 0 here, right? So in order to keep the same EB, average energy, you have to double this, right? So therefore, you have a 2 EB and root square, okay? That's the amplitude of this symbol. Now, what is different is that now let's look at the distance between these two symbols. Distance between these two. Now, what's the distance? Distance between these two symbols is now this much, right? Root square of 2 EB. So now let's go back to the antipodal case. Antipodal case, the distance was 2 times EB. 2 times EB, right? 2 times of root square EB. That was the distance at that time. But now in an orthogonal case, this is the distance. You see that now that the orthogonal case gives you the smaller distance, right? In this case, it's, the distance is now smaller than the case of antipodal. So therefore, you can expect a little bit higher bit error rate, right? Because of this distance, smaller distance. So therefore, if you do all the same thing, then now eventually you get this BER. Okay, bit error rate in the orthogonal case is going to be Q function of root square SNR. Okay, compared to the antipodal case, it was 2 times SNR in the antipodal case, but now in the orthogonal case, it's just the root square SNR. Okay. This picture, let me go back to this one. Okay, let's now see the QPSK case. Okay, this is no longer binary. We're going to think about the QPSK. So this is the constellation plot for QPSK, quadrature phase shifting. We have 4 different symbols, 4 different points, right? And we are transmitting 2 bits per symbol. For example, 0, 0, right? 1, 0, something like that. What we are interested in now is to look at the bit error rate of QPSK scenario. First of all, let's assume that we are transmitting this point. Okay? Maybe 0, 0, right? We transmit this point. Okay? When you transmit this point, there are 3 different cases of error. This point sometimes can be considered as dead points. That's an error, right? Possible reason is that you transmit this one, but because of noise, it is received somewhere here or somewhere here, right? Then those received symbols will be detected by this one. So that is the error. So this was a transmitted symbol, but this one is detected symbol. That's going to be error 1. Okay, error case 1. Second error case is that you transmit this one, but that can be considered as this one. That's the second case of error. Similarly, you can even think about the third case of error, right? You transmitted this one because of high noise. You received as this one, so it is detected as that symbol. That's going to be error. So there are 3 different error cases. But now, as I said, the error performance or bit error rate is a function of distance between 2 symbols. Now, look at the distance between these symbols, okay? And distance between this symbol and these symbols. Now we see that the distance between this one and this one are same, right? This one has the same distance. Therefore, the case 1 and case 2 have the same bit error rate. But this case, right, the third case, you see that this one, the distance is actually larger than this, right? This diagonal distance is actually bigger than this one. And therefore, you see some some other bit error rate. Okay, that's why because of this different distance, we can expect some different. Okay, in this case, it's lower bit error rate. Right. So what needs to happen is that we have to think about these three different cases separately. Okay, in order to make it accurate. But typically, right, we use a union bound to calculate the bit error rate. If you think about each of these separately, it's pretty much difficult. Sometimes it is impossible. Therefore, what you do is that you can think about one error case with a higher bit error rate. Okay? And then you just multiply the number of cases. So let's think about this case. I'm just giving you an example. Let's say this is QPSK. This QPS case is like symmetric, right? This one and this one, it looks like all symmetric. But as an example, just giving you an example, let's say I'm just thinking like, let's say these are my points. Okay, I'm gonna transmit one of these. Okay, just arbitrary constellation. In this case, right? Let's say I transmitted this symbol. There are error cases that this one is transmitted, but this one is received. That's one error case 1. This one is considered as this one. That's error case 2, case 3, case 4, case 5. There are 5 different error cases, right? If you consider each of them separately, then it's a lot of work. So what typically people do is that you pick one error case with a higher error. Which one gives you the higher error? Higher bit error rate. This is case 1, 2, 3, 4, 5. Which case gives you the higher error probability? Case 1, right? Because case 1 has a smaller distance. Smaller symbol distance gives you highest error, right? So if you pick just one case with a highest bit error rate, and then let's say that error rate is, let's say, EP1. This is the bit error rate in case of case 1, right? Bit error rate of case 1. And this case, probably you have the bit error rate of case 2, but you ignore all these things. You only consider this one, and you multiply 5, because there are 5 different cases. Okay, that's called union bound. Of course, this is what? This is the overestimated, right? The bit error rate is not as high as this, in fact, right? Because this case, right, P2, this bit error rate is actually lower than P1 because you have a large distance. Case 3 also, right? This one has a even larger distance. So therefore, P3, the error rate for case 3 should be lower than this one. But we do not calculate each one separately. We just pick the highest one and just multiply the number of cases. Therefore, it's overestimated. So this is called the union bound, right? We just simply add them together as a union, okay? That's called the union bound. So in this particular case, this is QPSK, so therefore you multiply 3. You multiply 3 with this case. What is this case? The first case. Among these 3 cases, the first case gives you the highest bit error rate, right? So you multiply 3 different cases, 3 times this one. So that's the union bound, okay? If you think about the high order modulation, this is the case of QPSK, but now think about 16 QAM or some 8 PSK or any other higher modulations, they typically do this union bound to find out the bit error rate. Okay, so far we looked at the case of 8WGN case. Okay, we didn't consider H so far, right? We only considered a 8WGN. Now, what we want to do is we want to consider a fading. Okay, we now have h. Earlier, we didn't have h, right? We only consider y equal to s plus n. Now, let's introduce the fading. We have y equal to hs plus n. Once you introduce the fading, right? Now, what can be changed is that when you have a BPSK, this BPSK symbol, your transmitter symbol is now multiplied by h. So therefore, original S1 was here, okay? Since this is a BPSK, original S1 was here, original S2 was here. But because of h, you multiply h to the s. So because of h, that symbol has now moved to here, HS1, and that symbol may be moved to HS2. This is just the example, okay? H here is just an example. H is random, right? This is fading channel, random fading. So at some point, maybe H can be somewhere here, right? So this is just the example. So when you have a fading like this, it's no longer S1 here, it's one. This symbol, S1, is now moved to HS1 right here. And then you have also noise, right? And from here, you are adding noise also. So eventually what you receive may be somewhere here, right? This much of is noise in that case. So that is eventually what you receive as Y. Once you do that, right? From this picture, what you see is that now we can think about HS1 and HS2 as the original symbol, and you can draw a Gaussian, okay? Same as what we did before. Then now you see that in this particular case, you see that the distance between these two has been increased, right? Because you see that the original one, H1 and H2 was, the original S1 and S2 was here. So compared to this distance, original distance, now since we undergoes H, this S1, S2 has been moved, has been rotated, and has been moved to here. So now we have to think about the new distance. This distance has been increased, like this, right? So therefore, you can expect a little bit lower error performance in this particular case. But as I said, at some other cases, right, the S1, S2 may be moved to here. Distance may be even shorter at some point, at some times, right? Okay, depending on H. Sometimes the distance is getting smaller, sometimes larger, sometimes smaller, okay? So given that, now you can think about exactly the same analysis as we did in case of AWGN, and you can do the same way. Eventually, you get the BER like this, okay? You see that the BER is a Q function, and inside the Q function, you have root square of E of B divided by N naught, and that times as H square. So compared to the AWGN case, difference comes from this H square, right? That's the only difference. We didn't have this one earlier. In the AWGN case, now we have H square. H is this one, right? What is H square? That's channel gain. Actually, H is channel gain. H squared is somehow a power from the channel. So therefore, if you consider these all together, EB times H squared divided by N naught, right? This whole thing, that's now SNR, receive SNR, okay? Because now we go through the H, okay? And you receive the symbol, this is received SNR after you go through H, okay? So we can see the BER is represented that way. Okay, so far we looked at the bit error rate for BPSK when we have single antennas, okay, called the SISO, single antenna at the transmitter, single antenna at the receiver, okay? And we also looked at the AWGN channel case which is y equal to s plus n. We also looked at the fading channel case, y equal to hs plus n. You see that in AWGN case, the BR is simply written as Q function like this. Okay? But when you have a fading channel, now it's no longer this one. We have to use the PDF of this SNR, and you have to do the integration like this, right? Okay? So for details about this, we're going to talk about in a minute. What if we have multiple antennas at the receiver? Let's say in case of SIMO, single input, multiple output. In that case, as I said earlier, your SNR, your output SNR right here, the output SNR is now doubled, right? That's what you see here, right? Your SNR, the output SNR, let's say you do the maximum ratio combining. Of course, that depends on what combining receiver you use at the receiver. We learned the 4 different diversity combining receivers, right? MRC, selection combining, and also equal gain combining, switch combining. So depending on which one you use, the output SNR is different. But the maximum ratio combining is the optimal case. So now suppose that you use maximum ratio combining here, then you get the optimal output SNR right here. The optimal SNR is going to be the double of the single antenna SNR. So that's going to be H1 square plus H2 square and SNR. Remember, in the single antenna case, the SNR looked like H square EB divided by N naught, right? That was a single antenna case. Now with the 2 antennas and also with the MRC, you see that we have two of them, right? So which means that we receive the double SNR or 3 dB gain. Okay, now we want to look at a little bit more detail about the some other type of modulation. So we want to look at the QAM modulation, but before we talk about QAM modulation, we have to understand the pulse amplitude modulation. So let's consider the Emory pulse amplitude modulation. Emory basically means that you have M points, right? QPSK means that you have 4, right? Binary is the 2, right? So M equal to 2 means binary, M equal to 4 means quadrature, and M can be any value. This is the case. This is an example when M equal to 4. And also the pulse amplitude modulation. What is a pulse amplitude modulation? This particular modulation basically differentiates all the symbol based on the amplitude. Amplitude, only the amplitude has the information, right? So that's what you see here. It can be like a voltage, right? You have some large voltage and some small level, even smaller level, something like that, right? Only the level or amplitude gives you piece of information. That's pulse amplitude modulation. So let's say, as an example, let's say M equal to 4. In that case, we are thinking about 4 symbol like this, and each symbol has a different amplitude. S1 has amplitude of minus 3D. S2 has the amplitude of minus D. Okay, S3D, S4, 3D. We have 4 different symbols. Now let's think about the error probability. Let's say you transmit this symbol, okay? And let's think about the error case. If you transmit this symbol, it can be error if you received this point, right? When you have, again, this is the case of AWGN case, okay? We ignored the fading, first of all. You transmit this one, and because of this high noise amplitude, maybe you receive this point. In that case, that received symbol is detected by S1, so you will get an error. Similarly, you transmit this one, but because of this high amplitude noise, this transmitted symbol is received somewhere here. That is an error, right? So for S2, we have 2 error cases, right? S1 can be received by S1, S2 can be received by S3. Both are errors, right? But now let's think about S1. We transmitted S1. When you transmit S1, there are only one error case, right? Because that can be considered, that can be received by S2. That's an error. That's the only one. So therefore, if you think about the error probability of S2 and S3, right? The probability that we have an error for these two symbols is the probability that noise amplitude is higher than D. Why is it higher than D? Because the noise, if the noise amplitude is larger than D, that means that you transmit here, but because of the high amplitude noise, your symbol is going here or going there, right? That's what I mean by noise amplitude is larger than D. If the noise amplitude is smaller than D, that means you are somewhere inside, right? Okay? And the probability of such error case is like the 2 times of this error. Whereas error probability of S1 and S4, you have only 1. Okay, it's not 2. Only 1, because there are only 1 error case. Okay? So these inner points, you have 2 of this error. For the outer points, you have only 1. Right? That's what you see here. If you transmit S2, right, then because of this Gaussian distribution, this is the error probability. That is another error probability. That's why for this inner point, we have 2 of them, 2 of the Q function. Okay, now think about the generalized M. Let's say we consider M, not just 4. This is just the example. Let's consider M. Then this is the error probability. What that means is you add these all together. Okay? If you think about that, now we have M symbol. Let's say we have M like maybe 64 symbols, right? In that case, again, you think about only the 2 outer points, the first one and the last one. Only those 2 points have only 1 error case. All the other inner points will have the 2 error cases, right? So you can separate like that. This one is all the inner points. So you have m minus 2 divided by m. M minus 2 is the number of inner points. Those inner points have this error probability, same as this one. 2, that's the outer points, the first one and the last one. Those 2 outer points will have this error probability, which is same as this one, right? And you add it together, and you take the 1 over m, because what we are interested in is the average error probability. So in order to take an average, you take the 1 over m, right? And you add it all together. That's going to be, and you put them together, that's going to be this one, right? This one is your error probability for this memory pulse amplitude modulation. Okay? Now let's extend to the memory quadrature amplitude modulation. This QAM, right? This memory quadrature amplitude modulation. This one can be considered as a 2 memory pulse amplitude modulation. You have one memory pulse amplitude modulation on this axis. You have the other m pulse amplitude modulation onto this axis, right? So in other words, we already looked at this one. This is a m pulse amplitude modulation. Now you think about another one here and put it onto vertical. That's going to be this one, right? You have one amplitude modulation here, another amplitude modulation there. Okay? So that's the memory QAM modulation. So you use exactly the same BER technique as we already looked at in the pulse amplitude modulation. Okay? Then you can get this one. The only difference is that in the earlier we used M, right? We have M symbols. Now in the QAM modulation, now you can think about m equal to L squared. And L is the number of number of symbols on one pulse amplitude modulation. In this case, L equal to 4, because for one M pulse amplitude modulation, we have 4 points, right? But we have to think about L squared because we have 2 amplitude modulation. So there are 4 here, and there are another 4 here. So you multiply that, that's going to be L squared. So total number of symbols in QAM is going to be L squared, but for each pulse amplitude modulation, you have 4 of them. So that's the only difference. So instead of, right? So what that means is if you think about a previous pulse amplitude modulation, you want to use L. You want to use L for each of them. Okay? You want to use L each of them. You want to replace M with L in here, right? And you have 2 of these, 2 of them, of this one, because we are thinking of 2 amplitude modulation. Okay? So you replace this L, the previous L, in the previous slide we use M, right? That M and this M actually is a little bit different. That M, the previous M is same as L in this picture. Okay? So earlier we have L right here in the previous picture. Let's go back to previous. We have L here, right? This is L and that is L. Okay? And that L now has to be changed to root square M. So you replace the root square M. That's the only difference. So you, instead of L, you put the root square M here, 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 and you think about 2 of them. So therefore, you think about half energy. Why is it half energy? Because we want to keep the same energy. Earlier, we have only one pulse amplitude modulation. So if you think about the energy, right, then we have average energy of E or B. But now we have to think about 2 pulse amplitude modulation. So each pulse amplitude modulation have to have a half energy. Half energy on this pulse amplitude modulation, half energy onto the other pulse amplitude modulation. So each pulse amplitude modulation has half energy. So therefore you see the half right here. Okay? That's the only difference. You have half energy for each pulse amplitude modulation, and instead of L, you use root square M. That's the only difference compared to the previous pulse amplitude modulation. All the other things looks exactly the same. Okay? But in this case, since we are thinking about 2 pulse amplitude modulation, now we have to think about a symbol error. Okay? Symbol error. Compared to bit error rate, symbol error rate actually is a little bit different, right? Especially when you think about high order modulation, symbol error rate probably is important. Symbol error. And let's think about the bit error. This is some of the basics, right? If you think about BPSK, in other words, 1 bit per symbol. In that case, symbol error rate, bit error rate is basically the same, right? Because 1 bit per symbol. Okay, anyway, it's the same. Now, then let's think about QPSK. This one is a 2 bits per symbol. So now we can think about bit error rate. We can also think about symbol error rate, right? So let's say, since we are thinking about the 2 bits per symbol, let's say this is 1 symbol, and this one has 2 bits. Let's say this is my bits. Okay, these 2 bits. This is 1 symbol. In that case, what is the symbol error rate? If this bit is changed to some others, like this one now becomes 1, right? Then it is a symbol error, right? It was 0, it was transmitted 0, but now it is 1, that's a symbol error. If this bit is changed, also that's symbol error. If both of them changed, again it's a symbol error, okay? So for any of the bits changed, that's a symbol error, right? So,
Bit error
Okay, now let's say, okay, let's say this is what we transmit. Okay, 0, 1 is what we transmit. Let's say we receive. We can think about 4 different cases, right? This is what we transmit. Now let's say this is what we receive. Let's think about 4 different cases. This one has 1 bit error. Of course, we are thinking about only 1 symbol. So there is a symbol error, right? In this case, no bit error rate, no symbol error. In this case, we have 2 bits, 2 bit error, symbol error. This case also 1 bit error, 2 symbol error, right? So for any bit you changed, okay, for any bit is error, you get the symbol error, right? So therefore, so this is the only case that you have no symbol error. So how can you find out the error probability, symbol error probability? Let's say you know the bit error rate. Then from that, can you find out the symbol error probability? This is the case. This is the only case that you don't have symbol error. So if you know the bit error, right? Since we are talking about 2 bits, right? Let's say PB is the bit error rate, okay? But we have 2 bits, right? And this is the case where you don't have any error, symbol error, okay? And this is the bit error probability. So now, since we have 2 bits, let's consider only 1 bit. Okay, first let's consider first bit. What is the probability that first bit is not in error? 1 minus PB, right? Let's now consider the second bit. Second bit also has the same error probability, right? So the probability that the second bit is correct is also this one. So if you multiply these two, this one is the probability that both bits are correct, right? That's the probability of this case, right? First bit is correct, second bit is correct. So this, if you multiply these two, that's the probability that both bits are correct. And if you take the 1 minus out of that, that means all the other cases. Okay? Simply speaking, right? That's the error case of symbol error. That's what you see here in this slide. So symbol error probability can be simply given as 1 minus bit error rate of square. Okay? Yeah. But as you see here, this one looks a little bit complicated. So what people do is that maybe we can try to do some approximation. Okay? Of course, you have to do a certain assumption. Let's say our M is big. Okay? We assume some big M. Okay? Then now let's think about this one. Okay? This one. Symbol error probability equals to this one. You can write this one as this way, right? So 1 minus square is going to be this, right? So now let's think about some big number of M. Let's assume that M is pretty big. It's pretty big. In that case, root 2 square M minus 1, maybe you can consider that the same as root 2 square M, because this is big anyway. Let's ignore this one, minus 1. Then this one can be canceled out, right? So the PB, original PB is 2 times Q function. So this original PB we can consider as a 2 times of Q function. Okay, this Q function. So let's put that inside. Now then, we can approximate as a 4 times Q function, that Q function, right? Minus 4 times Q function square. You know that Q function is like this, right? This much of error is a Q function. And if you do a square, probability square, that's so tiny. Okay, it's so tiny, right? When you do square of the error probability, it's so small. So we can simply ignore that. Then we can see that now this one can be approximated to the 4 times of Q function. That's what you see here. Okay, that's this one. 4 times of Q function. That's some of the approximation that a lot of people do. Okay, that's common approximation. Earlier, this case, right? This example that I show you is the case of 16 QAM. I chose the m equal to 16, right? This is the case. This is an example of m equal to 16. Okay, if m equal to 16, now as you see that we have this error probability, symbol error probability. If you think about the general modulation for any other modulation, not just the 16 QAM, but any other modulation, typically, right, the symbol error rate can be approximated into this form. Okay, PS, the symbol error probability, can be approximated as some coefficient alpha m times Q function root square of beta m, again another constant, and gamma s the SNR, symbol SNR, right? This is a common approximation that you can use for any modulation. So here's an example. Okay, here's an example. For some type of modulation, for example, QPSK or MQAM, now you see that this is a common assumption, right? Okay, so those are the common assumptions. Yeah, otherwise, if you want to make it accurate, it's so complex. Okay, using this approximation is very common. Once you use this approximation, now you see that my symbol error rate can be simply written as one Q function. Alpha m, beta m is just constant. Those constants depend on your modulation. Okay. But anyway, it's just a simple Q function, so it's much easier to start, right? Much easier to use. That's why a lot of people prefer to use this approximation. And these are the examples. Okay, let's look at the actual examples, some of the systems. We already looked at the maximum ratio combining, right? And this is the case of MRC. Now let's think about that we have m different number of receive antennas. Okay, we have m of them. Okay, we have m number of receive antennas. But when you do the MRC at the receiver, okay, mathematically, what that basically means is that your output SNR, which is gamma output SNR right here at the output, is simply a sum of each SNR from each branch, right? So here, right here, you get the SNR gamma 1. Okay? Here, from the mth antenna, you get gamma m. And you add all together, that's going to be your output SNR, right? Now you know that this gamma, each SNR is a random variable. That's a random variable, right? This is random because we know that H is random. So each one is considered as random variable. So now let's go back to mathematics, some basic probabilistic and stochastic theory. If you add multiple random variables, what happened to your PDF? What happened? So let's say this is what happened now here is that you are adding multiple random variables, okay, and define that as a new random variable, okay? You are adding multiple random variables, right, and make a new random variable. And now suppose that you know the PDF of each of these random variable, okay? Suppose that you know the PDF of each one. What happened to the PDF of the output? PDF of the new random variable. That's going to be the convolution. Okay? Right? Addition of random variables corresponds to the convolution of all the PDF. Right? You probably know that, right? Okay, so the output PDF of output SNR is the convolution of all the PDF. Okay, and now let's assume that each PDF is Rayleigh. In that case, Rayleigh looks like this, right? This is a Rayleigh PDF of SNR. Then what we need to do in this case is that we have to do a convolution of this one, m times. We have to do convolution with the m times, right? And this is the f1 gamma dot 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 to fm gamma. So we need to do convolution of this one m times. That's a pain, right? That's a pain. So what is the easier way? What is the easier way to find out the PDF? Huh? What is the easier way to calculate the convolution? This is a continuous domain, right? We are talking about continuous random variable. What is the easier way to calculate the convolution? Okay. So what is it? We can use a Laplace transform, right? Since we are talking about a continuous time domain, why is it better? Why? Why is it better to use a Laplace transform? But anyway, we'll talk about that in next slides. But anyway, the output PDF is the convolution of all these PDF. Okay? And now suppose that we found the PDF of output SNR. That actually happens to be this one. Okay, this is the output PDF. Okay, what I mean is that for each antenna, right here, let's think about the first antenna. Right here, we put that, we think this one as a gamma 1, right? Gamma 1 is the SNR of the first antenna, first received signal. And gamma 1, the first antenna, first received signal has this PDF. Okay? But we have m number of them, m number of this. And when you add it all together like this, then at the output right here follows this PDF. That's what I'm saying. Okay? So the output SNR of MRC follows this one. M, this is generalized scenario. Generalized scenario when we have m number of antennas. You can simply say that if you have two antennas, then you can put m equal to 2 right here. Maybe it's become a little bit simpler. But this is the generalized PDF of output SNR of MRC. Now what we need to know is the bit error rate right here. Okay? Bit error rate. So how can you find out the error rate? We know the PDF. So what we need to do is that using this PDF and put that into this equation, right? Here. Now in order to find out the bit error rate, now we have to assume a modulation. So let's assume a BPSK. Okay? Once you assume the BPSK, now this bit error rate, right? This is the bit error rate for 8WGN, right? That is going to be Q function, Q over root square 2 gamma. Gamma is SNR, right? That's the bit error rate BER for BPSK in 8WGN. Using that, and our actual PDF of gamma is this one, right? Because we just said that when you have MRC, this is the output SNR, right? That's the PDF of output SNR. So bring that and in here, that's going to be like this. Okay? So you need to solve this integral equation. Then your output looks like this. So if you look at some digital communications or any other book, right? Some Prokis book or any other book, if you look at some of the chapters, you will see this equation. any of the digital communications book, you will see this equation. How to get this equation is this way. Maybe some of you have some experience about CDMA, right? When you look at the CDMA system, you'll probably see the rake receivers. Rake receiver use the MRC. The difference here is that in this case, I use each one as an antenna, right? We are thinking about multiple antennas. Instead of multiple antennas, if you think about multiple rake receivers, right, then all the other analysis, mathematical analysis, apply exactly the same way. Okay? In the rake receiver also do the MRC. Okay, if we have time, maybe in some time later, we can probably talk about that when we talk about multiple access scheme. But anyway, what I'm saying is that it doesn't matter whether multiple antenna system or rake receiver or any other system. In case of MRC, you have exactly the same analysis like this. Okay, and that's going to be your performance, bit error rate. Now maybe you may want to ask a question. How do you solve this? Right? You may want to ask that question, right? I'm going to answer that in a minute. But anyway, for now, let's assume that you can do that. And this is the solution. Okay? I'm going to talk about that in a minute. And here is the graph. Here is the BER graph of this one, right? This is the BER that we just get. Okay, we got this one. And you put the m equal to 1, which means the single antenna case, you get this BER. If m equal to 2, 2 receive antennas, you get this one and this one. What you can see from this picture, you see the different diversity order, right? You have single antenna, this is the slope of diversity order 1. This is the slope of diversity order 2. This is the slope of diversity order 4. So if you increase the number of antennas, you see the different diversity order, the different slope. Okay? You can actually run MATLAB to, you can code this one, right? And make your own MATLAB function, and you can, plot it. You get exactly like this. As a second example, now let's think about another system called the selection combining. Remember, selection combining is choose the best one, right? You choose only one among all these. Again, let's assume that we have m number of antennas. Okay, we have m number of antennas. Our goal is to choose the best one. We are choosing only one, the best one, out of this m. Mathematically, it can be written this way. The output SNR right here, output, is going to be the max out of these m different SNRs. So you're going to choose only one, the maximum one, right? So mathematically, it's written this way. So how do you approach for this one? Going back to MRC case, right? How we started was that we consider each one as a random variable, right? And you are thinking about the sum of random variables. When you have a sum of random variables, that corresponds to the convolution of each PDF. That's how we started. Now in this case, right, we are looking at the different function. It's not summation anymore. We are choosing the best one out of these random variables. Again, these are the random variables. Among these random variables, we are choosing the best one. In that case, right, we are starting a little bit differently. We are starting from the CDF, cumulative distribution function. Okay? And we are starting from CDF, and the probability that maximum of this, the probability that the output SNR is less than certain value is written this way, because the output SNR is same as this one, so you can put this one in here, okay, and this one, and that is the multiplication of all the PDF. So detail about all the CDF, right? So the output CDF is the multiplication of all the CDF. So detail about these things, I'd like to encourage you to look at the probability and stochastic book. I can talk about the details, but it's a little bit complex. But let me simply explain what this basically means. Okay. Now, simply speaking, right? Let's think about only two, gamma 1 and gamma 2. Okay, these two are random variables, and what I want is the output, and that output is the maximum of these two random variables, right? I'm just considering m equal to 2. In that case, your output is actually, it's going to be either gamma 1 or gamma 2, right? If gamma 1 is higher than gamma 2, then you choose gamma 1. If gamma 2 is higher than gamma 1, then you choose gamma 2, right? Because that's what you do in the maximum. So now let's plot this one into the gamma 1 and gamma 2, just to visualize. This case, right, gamma 1 is higher than gamma 2. That's the case of this area. Okay? That's the case of this area, right? And this second case, gamma 2 is higher than gamma 1, that's the upper case. Okay? Now the the output, SNR, is equal to the gamma I, gamma 1. And now as you see that we are talking about a CDF. Okay? So therefore, we have to think about the probability that your output is less than gamma. So let's think about that one. Your output is less than gamma. That's a CDF. And if gamma 1 is the gamma 2, if gamma 1 is higher than gamma 2, then my output is going to be gamma 1. That's what I said, right? If the gamma 1 is higher than gamma 2, my output is going to be gamma 1. So I replaced my output into the gamma 1. That's this one, right? And as I said, gamma 1 equals gamma 2, meaning this area, the lower area. And this probability, gamma 1 is lower than gamma, is something like this, right? Let me pick my gamma. Let's say here's my gamma. Then the probability that my gamma 1 is smaller than gamma means that here's the gamma. So this is my area. Okay, that's my area. That's the probability of this region, right? Now let's consider another case. If the gamma 2 is larger than gamma 1, in that case, same way, I'm considering this one, right? Because gamma 2 is larger than gamma 1, so I choose the gamma 2. And gamma 2 is less than gamma. That's going to be this one. Okay? So eventually, this one corresponds to this area. That area, in fact, corresponds to the multiplication of these two. Okay? And this one is the CDF of gamma 1. This one is a CDF of gamma 2. So that's why your original output of gamma CDF, that corresponds to the multiplication of these two. Okay? Same way, you can do the same thing for m different random variables. Exactly the same way. Okay? So some of those techniques you can refer to the probability stochastic book. So that's how we can get as a CDF. So you get the CDF like this, right? And then now what we have to do is we take derivative with respect to gamma, right? Try to find out PDF. You first find the CDF, and then you take the derivative of that with respect to gamma. Eventually, you get the PDF. And if you assume a Rayleigh distribution, that PDF looks like this. This is the PDF of selection combining case. Let's compare with MRC. In MRC case, the PDF looks like this. PDF of SNR looks like this, right? But in case of selection combining, our PDF looks like this. So what I'm saying is that if you design of your own system, then using some of these techniques, mathematical techniques, and try to find out the PDF of the PDF of output SNR of your system, then you can get some PDF, right? And then bring this PDF into here, right? And use the same technique like this calculation, which is exactly the same way as we did for MRC case. Then you get the BER. And for the selection combining, we also plot the BER with a different M value. You see that, you see that these BER pictures. Here again, as you see that if you increase the number of antennas, you see the different slope, meaning that different diversity order. So this is what we plot this one. Okay, for the next three slides, I guess 4 slides, are showing some of the details of how we can actually solve that integral equation. Okay, we haven't talked about yet is that how to solve this integral equation, right? This one we didn't talk about yet. Okay, so that's what we're going to talk about. As I said earlier, this is the approximation that you can use for BER for any modulation, right? For any type of modulation, you use different alpha. For a certain type of alpha, for a certain type of modulation, you have different alpha, different beta. But most of the modulation, the BER can be the symbol error rate can be approximated by this single Q function. Okay, and this f of gamma PDF depends on your system. If you use MRC or if you use other system, you have a different f of r. This part depends on the modulation you use. This part depends on your system. Okay, so you put that together, then you get finally the BER or SNR or symbol error rate. Now, the problem. Let's go back to our case, right? MRC case. The problem about this one, right? We have to solve this integral equation. Look at this one. This is a polynomial, right? And the bottom here, this is just a coefficient. We can ignore this one, right? This is the factorial. This is just the power of this is just constant. So these are constant, no problem. And this is a polynomial, an exponential function. So integral of exponential, it's easy to do it, right? So we have no concern about these things. What is problem is the Q function, okay? Q function is the main problem. For any kind of error rate analysis, you will have a Q function, okay? But that Q function is a problem. So in other words, you always see this kind of analysis, this kind of equation when you try to look at the bit error rate. Any bit error rate equation, you will see a Q function. So that's a problem. Because Q function is defined this way, right? This is the original definition of Q function. Q function is the probability that your random variable, this is a Gaussian random variable, Gaussian random variable is higher than your parameter or argument, right? So that's this probability is the Q function. And mathematically, that is defined by this way. This is a Gaussian distribution with the variance 1. And that's the argument. And that is the integration between the argument to the infinite. So this argument, right? This argument is in the lower limit of the integral. That's the big problem. Because put this one in here, right? Let's replace this Q with this, because that's the original definition. Put this one in here. Now what you see is that this is the integration. We have a double integration. Integration has the argument as a limit. Okay, that is a big problem. Therefore, it's very difficult to do it. Therefore, this guy, here's a reference, right? This paper proposes some very nice mathematical tool which replace this Q function, which rewrite this Q function into another type of integral. So this is called the alternative Q function. This is again Q function, but this is the original definition of Q function. But instead of defining the Q function this way, he defined it differently. This one carefully, right? This one looks almost the same as Laplace transform. Just think about that this is your time domain signal, any time domain signal. And then you take this kind of integration that looks almost same as Laplace transform. Only difference comes from the sign. Original Laplace transform has minus st. Okay? So that minus is the only difference. Other than that, it looks almost alike, the Laplace transform. So this moment generation function, in fact, can be considered as the same as Laplace transform of this PDF, but only the argument reversed in sign. Okay? Instead of s, we use minus s. But still, the looks almost same as Laplace transform of this PDF. Okay? In other words, since this one looks almost same as Laplace transform, what we can use is that if we use the PDF, if you know the PDF, then we can simply find out the MGF by just looking at the Laplace transform. Laplace transform, you have a lookup table, right? You can easily get the lookup tables. So by just looking at the lookup table and try to find out this signal, then you immediately get the MGF of this PDF, right? By looking at the lookup table. Example, here's the example, right? This is a Rayleigh fading distribution. This one is a Rayleigh distribution. And you put this Rayleigh into here and calculate this integration, then you get this MGF. Okay? If you want, then you can calculate this integration. Or another way to do it is that you can find this equation, this PDF, into the lookup table, Laplace transform lookup table. Then you'll see this one. Of course, you have to be careful about this sign, right? But anyway, you will see this one. Same way, right? If you find out this one, this is called a Nakagami fading channel. This is another type of channel. Okay, there's a Rayleigh channel also, right? We typically think about multiple different channels. Rayleigh channel is most common. Some people use a Nakagami channel. It's more generalized channel model. Because this is a more generalized channel model, this one looks a little bit difficult, a little bit more complex. So if you find this one in the Laplace transform lookup table, you will find this one. So this one, right, in PDF domain, it looks pretty complex. But look at it in MGF. It looks pretty neat, right? So sometimes it's much easier to use the MGF. So let's see what happened here. Let's revisit of symbol error rate of m-QAM over generalized fading channel. Okay, this is a general scenario, and this one basically shows you how we use MGF. Symbol error rate can be defined this way. We can start from the symbol error rate, original symbol error rate of AWGN channel. This is the symbol error rate of your modulation in AWGN channel. Depending on your actual modulation, you find out your own alpha and beta. Okay, and this is the actual BR in AWGN channel. But we are not using AWGN channel, right? We are using some generalized fading channel. So we have to write some fading channel profile here. Okay. This is your fading channel profile. It can be a Rayleigh channel, it can be Nakagami channel, or it can be the SNR from MRC, whatever you want, okay? Whatever the output fading channel you want, you put that in here, okay? This is the modulation and the PR of that modulation over AWGN. Now, as I said earlier, we can replace this Q function using the alternative Q function, okay? Then this Q function can be now replaced into this way. Okay, I just use the alternative Q function. Then you see this one, right? And then let's switch these two integrals because this integral has the 0 to infinite. It's a little bit easier to deal with. So let's switch it. Then you'll see this equation. I just simply switch it, right? once you switch it, now you see that you look at the inside, the inner integral. This inner integral looks like Laplace transform or MGF. So this integral, inner integral now can be changed into MGF. The only difference is that in earlier MGF, right? Let's go back here. I use S gamma. Looks pretty simple, but in this case, instead of S, I use this one, right? This whole thing is same as S, minus beta divided by sine square. That's same as S. So consider this one is S, then you get this one. This is minus S, right? So it's the same way. So you can simply write this complex thing into this one. So this is a little bit easier. It's much easier way to write this singularity rate. Okay? So far here in this equation, I didn't assume anything about the Rayleigh channel. About the channel. I just said as a general fading channel. I didn't make any assumption. Just to give you an example, right? Now let's assume a BPSK or a Rayleigh. This is a little bit more specific example. So since we use a BPSK, now our BER, this particular Q function is now changed to Q root square 2 gamma, right? This one is now simplified into this one. Because I said the BPSK, right? I consider BPSK, it's now simpler. And also I said the Rayleigh fading channel, so this F of gamma is now Rayleigh channel. So once you put this together and also use the alternative Q function for this guy, then I can write this one as this way. Using the same technique, I switch these two integrals, okay? And then I can write it this way. That's what I did, right? I switch it and put these two exponential together. There's one exponential here, another exponential function here. We put together, right? And bring this constant, right? This constant, bring this constant to the front with this one. Then you can rewrite this one into this way. This is just a very simple exponential function, right? So you can easily calculate exponential function. Then this inner integral now can be calculated, and you can eventually get this one. Okay? Now you see this one. This is a very simple integral. Okay? And if you solve this simple integral, that's going to be this one. So now maybe you want to ask another question, right? How do you calculate this integral now then, right? That's your question. The answer, look up your book, okay? A lot of people, a lot of research scientists have solved so many of different this kind of integration, and they gives you the closed form for each of these integration. So for this one, right, if you want, then you can run the Mathematica, okay? Not MATLAB, since MATLAB cannot calculate the continuous variable. You can run the Mathematica to calculate this one if you like, but you don't have to. There's a lot of good references, good books that shows you all these different types of integration and shows you the exactly closed form. So you can refer to that book. Once you reach this kind of equation, that's the end. Okay? Once you reach that, then you can simply write it this way by looking at the book. Okay? That book will tell you the exact closed form for each of these. So your goal is to reach to this stage. That's your goal. Okay? And if you look at here, right, it basically shows that sine square divided by something plus sine square. When you analyze the BER of some system, then you probably see this one often. Okay? So maybe you may want to get used to it. I guess this last slide. Now let's think about a little bit more advanced scenario. And in this scenario now we'll revisit the MRC case. Okay? So BER of MRC with BPSK, and let's assume the Rayleigh. Remember that in case of MRC, this one was our output SNR, right? This is the PDF of our output SNR, remember? Since we are talking about multiple receive antennas, each receive antenna is going to be Rayleigh, but when you apply the MRC, you are adding all these SNRs, right? This is the PDF of output SNR. So let's put this one into here. Okay, bring this one, because this is the PDF of output SNR. Bring this one in here, and use the BPSK PER here. Okay, bring this one here. Then you can simply write it this way. Okay. Again, we want to use alternative Q function for Q function. Okay, let's switch. Let's replace this Q function with the alternative Q function. Okay, and then bring this coefficient to the front like this. Okay, and let's switch these two integration same way as we did before. Then now you see this one. Okay. And now from here to here, I just rearrange it. So basically, this one and this one same. Basically, I just rearrange it just to look at it a little bit more clearly. Once you look at it this way, then I can consider this one as S, right? This is my S. Once you do that, now what we want to do is that from here to here, right? My inner integral looks like Laplace transform, because I consider this one as S. Okay? This one is S. Then you're thinking about the Laplace transform. Okay? Simply take the Laplace transform and look up the Laplace transform table. Okay? Let me show you one of the Laplace transform table. Here is you can get this one from online, right? I just searched it on the Google last night and found this Laplace transform lookup table somewhere online. So this is a table of Laplace transform, right? Written by this guy. And you see that when you have this f of t, you take the Laplace transform, you get this one. This is Laplace transform. Okay, this is the time domain. So you have so many of them like this, right? So you can refer to this. Now, for us, what we need, in fact, is this one. Look at this one, right? This one looks almost alike of our function. And that Laplace transform looks like s plus alpha to the power n. Okay, that's the Laplace transform that we want to use for us. That's the case of our system. Okay, so that actually looks almost like this. So when you take the Laplace transform now, this one is going to be like this, right? That's our Laplace transform of this one. So if you rearrange that, then it shows as this one. Okay, and that's our final goal. Once we have this one, then again you can look up to the book. Okay, some appendix chapter. That chapter shows you exact closed form of this integral equation. That happens to be this one. That's how we get this. So if you go back to the MRC slide, okay, go back to the previous slide with the MRC, you see this one. Okay, we get the exactly same BR result using MGF, moment generation function. One thing that I want to tell you about that is that if you look at this one, right? Look at this one. This one reminds us one thing. Okay, look at this one, right? This one is the something to the power of m. So let's go back to the MRC case. Okay, just the final words. Not here. Okay. As I said earlier, when you add multiple random variables, that corresponds to the convolution of PDF, right? When you have a convolution of PDF or convolution in time domain, okay, easiest way to calculate the convolution is take the Laplace transform. So when let's suppose that this is time domain signals. Okay, you have m different time domain signals. When you do the convolution, what you can do instead is that you can take the Laplace transform for each of them. Okay, for each of them you can take the Laplace transform and go to the S domain, and then what you do is the multiplication, right? Multiplication in Laplace domain corresponds to the convolution in time domain. But in this case, right, I assume the same PDF for everyone. Okay? So what I need to do in order to find out, in order to calculate this convolution, what I need to do is that I need to find out the Laplace transform for one, and then I take product m times. I just to the power of m, right? That's what I did. Okay? Well, that's much simpler, right? How can you do the convolution of this one m times, right? That's very difficult to do it. But if you bring this one to the Laplace domain, that's even easy, right? We can look up the Laplace transform table, and then you can take the power of m. That's gonna give you the PDF. That's what you see here. Okay? That's why you will see the power of m right here in the Laplace domain. Okay? As I said, we are talking about the MGF, right? And as I said earlier, MGF is almost same as the Laplace transform. Okay? So you basically take the MGF to the power of m. That corresponds to the MRC, where you basically add multiple random variables. And that's a convolution. Okay, that's it for today. Any question?